This video presents the Monte Carlo method to analyse the uncertainty of a model's prediction. It consists of two parts. In part 1, the background of the Monte Carlo method is given. The Monte Carlo method refers to solution techniques that use random numbers and probability statistics to investigate problems and come up with approximate solutions. Early on, the Monte Carlo method was used by physicists to approximate the calculation of higher-order integrals. A Monte Carlo analysis performs multiple model evaluations of a probabilistically selected model input, and then uses the results of these evaluations to determine the uncertainty of the model predictions. The integral of a function f, u1 up to ud, is considered, depending on d variables u1 up to ud, over the unit hypercube 0, 1, d. It is assumed that f is square integrable. The law of large numbers, a central limit theorem, ensures that the Monte Carlo estimate converges to a true value. In summary, the Monte Carlo method is all about an efficient calculation of higher-order integrals. Since most of the time a finite sampling number n is used, there will be an error in the Monte Carlo integration of multidimensional functions. Sigma f is the standard deviation of the error and can be approximated using a sample variance. This means that the higher the n, the lower the error. The goal of an uncertainty analysis is to determine the uncertainty in the elements of y that results from uncertainty in the elements of x. The VARY and EY require the integration of fx over the joint multidimensional probability distribution space of x. Hence, the use of Monte Carlo simulations to compute the integrals of VARY and EY. In this video, the application of the Monte Carlo procedure is presented to calculate the uncertainty of the model output given the errors in the parameter estimators obtained in example 5.4. The workflow of the Monte Carlo method contains 4 main steps. In step 1, the inputs that have uncertainty are identified, and a range or distribution for each uncertainty input is defined. For example, the normal distribution, uniform distribution, etc. The output from the parameter estimators, for instance from the bootstrap method, can be used as an input in this example. In step 2, the sampling number n, for example 50, 100, etc., and a sample from the input space using a sampling technique are defined. The most common techniques are random, like the Latin hypercube sampling, etc. The output from this step is a sampling matrix, xn, xm. N is the sampling number and m is the number of inputs. In step 3, we perform n simulations with the model using the sampling matrix from step 2. The outputs are recorded in a matrix form to be analysed later. In step 4, the outputs are plotted and the results are reviewed. For instance, the mean, the standard deviation or variance, and the percentiles, e.g. 95% for the outputs, are calculated. Then the results are analysed within the context of the quality of parameter estimation and the prediction uncertainty of the model. The analysis can be performed through several iterations for a different framing if necessary. An application of the Monte Carlo procedure is presented in this video. Every Monte Carlo analysis needs to have a framing. This means to define the boundary conditions and assumptions for the analysis. An absolute uncertainty analysis does not exist. Rather, there is a context in which the uncertainty analysis is performed. Following the problem statement, the uncertainties are considered in the estimated AOB parameters. The mean and standard deviation estimates are taken from the bootstrap method, together with their correlation matrix. These data are saved in the boot AOO data file. It is assumed that these parameters follow a normal distribution with the covariance matrix obtained from the bootstrap method. The marginal distributions of each parameter are shown. These plots can be seen in the example 5_6.m script file. The parameters are defined to follow a normal distribution. The input uncertainty space is represented by a joint multivariate normal distribution. Hence, a multivariate random sampling technique, MVRND, is used to sample from this space. The output from this step is a sampling matrix, xn, xm. N is the sampling number and m is the number of inputs, and the content can be visualized by plotting. These are implemented in the example 5_6.m script file. In steps 3 and 4, n-model simulations are performed, using the sampling matrix from step 2, xn, recording the model outputs in a matrix form and plotting the results. From the simulation results, the mean can be calculated, as well as the standard deviation and percentiles, within, for instance, 95%. The results show that the uncertainty in the model outputs is low. This means that the errors in the parameter estimators have a negligible impact on the uncertainty of the predictions of the model. These are in agreement with the linear error propagation shown in example 5.3. These are implemented in the example 5_6.m script file. As always, caution is recommended when applying the Monte Carlo procedure to an uncertainty analysis. It should be kept in mind that this analysis is open-ended and relative to the framing. Thus, it can be misleading if it is not used appropriately. A more thorough discussion can be found in the publications of Sin et al. 2009 and 2011. The following references are recommended for further reading. In the current folder, 4 files to implement the Monte Carlo workflow in MATLAB can be seen. The main file is example 5_6.m, which executes all the workflow, including the subfiles. boot.aoo.mat includes the summary of the results of parameter estimation. This was obtained using the bootstrap method shown in the video of the example 5.4. This file contains the parameter uncertainty, for instance the parameter covariance matrix and their empirical distribution functions. This will be used as input to step 1 of the Monte Carlo workflow. init_d_cond.m contains the initial conditions and nominal values for the model parameters. initmod.m is the file that contains the nitrification model. To open the content, please double-click on the main file, example 5_6.m. First, the highlight mode is selected to execute the file step by step. Click Run and then click Step. This function will clean the workspace and figures, if there is any. Next, the parameter estimation summary file boot.aoo is loaded. This file contains the uncertainties of the parameter estimators, summarized in the p-min matrix obtained from the bootstrap method. Plot and visualize the content of input uncertainties and save the figure. Next, perform the sampling to be used in the Monte Carlo simulations. First, specify the sampling number as 100. Then, calculate the mean and the covariance of the input uncertainties. Use the mvrnd command to perform a random sampling from the multivariate normal distribution defined by the mean and covariance matrices. Plot and visualize the sampling results. Notice that the correlation between the input variables is preserved properly as expected. Next, save the figure for later use. In step 3, perform the Monte Carlo simulations. Define a loop to execute n model simulations. In each loop, read a row from the sampling matrix X. Update the parameters of the model and solve the model. Record the output of the model in Y to use it later. In step 4, plot the Monte Carlo simulation results. Plot them first as raw data. Calculate inference statistics, such as the mean and 95% percentiles, and plot them. This concludes the analysis of the Monte Carlo simulations. Simply, the input uncertainty in P-min was propagated to output uncertainty Y. The results can then be interpreted using knowledge on process engineering. The uncertainty bounds, 95 percentiles, are low for most of the outputs. This means that the input uncertainties do not cause any significant uncertainty in the model output.